This video is intended to be a very quick pause and check in with the major topics that we've been looking at in our study of differentiation of multivariable functions, and then I will give you a quick preview of what's to come. So there's not really any new information here. I just want us to summarize the biggest ideas that we've seen so far. So at the top, I'm going to talk through the most general notions that we've had. And then down here in the lower half, this is looking more at scalar valued functions, which we've been focusing on recently, and which will continue to dominate most of our conversations. So first, let's just start with a general setting. Suppose f is a function on some open domain A, which is a subset of Rn, and f sends you to Rm. Assuming m is greater than 1, you could say that f is a vector valued function on n variables. If m equals 1, like it does down here, we would say that f is a scalar valued function of n variables. If f is differentiable at some point p in its domain, then our first order approximation for f is given by this expression. We've seen this before, although I think I'm giving it a new name. So I think from here on out, I'm going to call this T sub 1, T for Taylor. So that will make more sense in an upcoming video why I'm going to name it that. But this is our familiar first order approximation for f. I've said that this is the first order approximation given that f is differentiable. Let me now quickly write down what it means to say that f is differentiable at p in terms of T1. So let me just kind of write it down as quickly as I can. I would say that the distance between f of x and T1 of x vanishes so fast that when you compare the ratio of this expression to the distance between x and your fixed point p, overall this ratio goes to 0. Sorry, I really struggled to write that down, but this ratio goes to 0 as x approaches p. Okay, so it's like the gap between our true function and its first order approximation vanishes really fast. So f is being really well approximated by its first order approximation. That's what it means to say that a function is differentiable. It has such a good first order approximation. For the general setting of a function which takes us from Rn to Rm, this is completely valid, but let me just name it something special. If f is a map from R to R, so n and m are both 1, this would be the tangent line at the point P, f of P. And if f were a map from R2 to R, so something like z equals f of x and y, this would be the equation of the tangent plane at the point P, f of P. So there are special familiar objects that we often work with in calculus, but of course it generalizes in this way. All right, so df at p here, this is a linear transformation. We've talked a lot about this, so I'll probably go through that pretty quickly, but it's a matrix. I mean, it's a linear transformation, so to that we associate a matrix. It would be m by n if f is sending us from Rn to Rm. And what does a linear transformation do? It just multiplies vectors on the left by the associated matrix. Okay, so this is kind of where we started our conversation of differentiation, our conversation on differentiation. More recently, we've been focused on scalar valued functions. So the codomain for f is one-dimensional. And in particular, we've been looking at C2 functions so that we could start thinking about higher order derivatives, namely the second order derivative. So first, let's just say that if f is a scalar valued function, then the Jacobian matrix, so this familiar Jacobian matrix, it turns into a row, a 1 by n row. If you flip that, if you take the transpose, then it's an n by 1 vector, and that has a nice common name that we see a lot, and that's what we call the gradient. So I just wanted to make that note here. Additionally, it makes sense to talk about higher order derivatives when f is vector valued, but here in real analysis 2, we're going to talk about the Hessian matrix, the notion of like a second derivative operation for scalar valued C2 functions. So for a scalar valued function of n variables, our Hessian is n by n, and assuming that we're working with a C2 function, which we will in this course, it's also a symmetric matrix. Okay, I skipped this. Just like the Jacobian matrix is a linear transformation, it acts on one vector. The Hessian matrix is a bilinear form. It acts on pairs of vectors. Kind of alluded to the fact that if you were looking at a third order differential computation, it would be a trilinear form acting on triples of vectors. So that's how you want to think of building up this idea of the total derivative for subsequent levels of differentiation. All right, this is a summary of the major ideas. I didn't put on here the chain rule. We spent a lot of time with the chain rule. You can think of that as a technique to calculating derivatives. We also talked about partial and directional derivatives, but hopefully you feel ready to go with all of these concepts. In a moment, let me just look ahead at some upcoming topics which we're going to discuss. Kind of now that we have this machinery under our belt, we can start thinking about like what differentiation is used for. As promised, here's a look at some upcoming topics for us. Each of these could be a very large topic in its own right. So we are going to do like a survey of topics related to differentiation of multivariable functions rather than a deep dive into each one. So next up would be Taylor polynomials. We have secretly been looking at a Taylor polynomial for a while. That's the first order approximation. That's the first order Taylor polynomial. That's why a moment ago I was calling our familiar linearization formula T sub 1. So next we'll talk about T sub 2, and for that we'll bring in the Hessian matrix. Optimization, of course, is a big topic. We will have at least one video, but maybe two on that. And for optimization, the idea is developing a sense of first and second order tests for multivariable functions analogous to what you're familiar with in single variable calculus. I'm not going to go into a deep dive in real analysis 2 on linearization of differential equations because that could be a class in its own right, but I do want to show how to tie the Jacobian matrix and the kind of ideas that we've been working with to the study of differential equations to help you make the bridge between these topics. Then we have a pair of very famous results, the inverse and implicit function theorems. So the inverse function theorem is like a generalization of the horizontal line test, if you will. So, if you want to say, hey, can this function where y is a function of x be inverted to the perspective that x is a function of y, if you're looking at a graph of such a function on the xy plane, you would just draw horizontal lines and see if the inverse function would pass the vertical line test. Okay, I'm going too into detail, but let me say that we will generalize that idea to functions from, say, Rn to Rn, basically. The implicit function theorem is related to the inverse function theorem. It's basically like when can you take an equation and view that equation as defining the action of a function. For a very quick example, because I want to give an example, but I also don't want to go too much into this right now. It's like if you have x squared plus y squared equals 1, that's the graph of the unit circle in the xy plane. That does not define a function because it doesn't pass the vertical or horizontal line test. But we just look at, say, the upper semicircle. We could think on that upper semicircle that y is a function of x. There it would pass the vertical line test. So we're going to generalize that idea. Like, can you zoom in and view an equation as a relationship which is like a function? We will generalize this idea with the implicit function theorem. Okay, I will say no more. And then, of course, I might add to this list, maybe soon, maybe in the future, we can come up with other topics to consider through the lens of differentiation. I will mention, although I did not add it to this list, that when we look at integration, we have this famous theorem called the change of variables theorem. And when you study that, you bring in a Jacobian matrix. So that's going to be another application of the theory of differentiation for multivariable functions, but one which won't come up for a while because we'll have to first define Riemann integration for, say, a scalar value function of n variables before we bring that in. So I didn't add it to this list because it's in the distant future, but it's just an example of another place where something like a Jacobian matrix crops up. All right, I think I will wrap this up here. And in the next video, we will talk about Taylor series.